Well, having learned something called the Euclidean algorithm, now we're going to learn something called the extended Euclidean algorithm. Here's the basic problem we want to solve. Bézout's identity guarantees that if a and b are not both 0, there have to exist integers x and y so that the GCD of a and b can be written as ax plus by. Can you actually, however, find what integers x and y work? Are there multiple solutions or is there only one? If there are multiple solutions, can we find them all? Well, here's going to be a theorem that allows us to solve that question. Suppose a and b are not both 0, and let's also suppose that I have found two integers x0 and y0, which solve the desired equation. ax0 plus by0 is equal to the GCD. So I have found one solution to my desired equation. Then the set of all solutions, ax plus by equals the GCD of a and b, are exactly given by letting your x be of the form x0 plus k times b over the GCD, and y being y0 minus k times a over the GCD, where this x0, y0 is the one solution you found, and k is any integer you want at all. Specifically, if you find one solution, then any pair xy of this form will also be a solution, and any possible solution must be of this form. But this also tells you that as soon as you find one solution, there must be infinitely many because k can be any integer. Note that one of these has a plus and one of them has a minus. A lot of people get very concerned, what if I don't remember which is which? It doesn't matter. As long as you put one of them with a plus and the other with a minus, you'll be fine. Imagine, for example, k is 5. You get x0 plus 5 stuff, and here you get y0 minus 5 other stuff. What if you replaced k being 5 with k being negative 5, because k is allowed to be any integer? Then you'd get x0 minus 5 things, and here you'd get y0 plus 5 things. Since k can be any integer, including positives and negatives, it doesn't really matter where you put the plus versus the minus sign, as long as you remember that they have to be different from one another. So for example, suppose a is 7 and b is 5. The GCD is 1, that's a quick computation. Can I get 7 times something plus 5 times something else to equal the GCD? Yes. 7 times negative 2 plus 5 times 3 is equal to 1, and I found that just by sitting and thinking about it for a bit. Then the set of all solutions, well, notice, if I let a be 7, then here is one particular x0, negative 2, and b is 5, so here is one particular y0, 3. So x must be of the form, the one value of x I found, plus 5 times k over the GCD, which is 1, so 5k over 1. And y must be of the form, the particular y value I found. Here I put a plus, so here I put a minus. 7 times k over the GCD, and again the GCD was 1. So for example, pick k equals 4. Then negative 2 plus 20 gives me 18, and 3 minus 28 gives me negative 25. And if you take x equals 18 and y equals negative 25, it will also satisfy 7x plus 5y equals 1. So any choice of k that you could possibly make, plug it into here to get a pair x and y, and you will solve 7x plus 5y equals 1. Well, let's prove that this technique works and also gives you the only possible solutions. So we start off by assuming that we happen to have one solution, ax0 plus by0 is the GCD. Next, what you want to show is that if you pick an integer and set x and y to be these forms here, you will also solve ax plus by equals the GCD. This is half of our proof. If you have one solution, then we're going to show that any pair of this form also solves our desired equality. Well, it's just a matter of computing. Ax plus by, well, here's x, here's y. If I distribute all of this out, we get ax0 plus akb over the GCD, b0 minus akb over the GCD. Notice that these two terms cancel out, leaving behind just ax0 plus by0, which we assumed was equal to the GCD. So if I assume that I have one solution and I pick any x and y of this form, that x and y will also provide a solution. So all choices of x and y that match the form above will form a new set of solutions. But are those the only solutions? Okay, so let's continue. Let's suppose that ax naught plus by naught does equal the GCD, and let's also suppose that I found another x and y that solves the desired equality. We need to show that x is of the form we desire and so is y. Well, if I cut out the middleman and just say ax plus by equals ax naught plus by naught, I can move the a terms to one side and the b terms to the other and get this. Notice that I factored the a out and I got x minus x naught. On the other side, when I factor the b naught, you get y naught minus y. They're in slightly different orders. Well, a and b are both multiples of their greatest common factor. So let's write that a is the GCD times m and b is the GCD times n. And remember, once you factor out the GCD, what's left behind must be relatively prime to one another. So the GCD of m and n must be 1. So a times x minus x naught is equal to b times y naught minus y, where we've replaced a is this product and b is this one. But now I can cancel out the shared factor of the GCD. So m times x minus x naught is equal to n times y naught minus y. But observe, these two numbers are equal. M is definitely a factor of the number on the left, and since it's the same number as this right, then m must be a factor of n times y naught minus y. And similarly, n is definitely a factor of this thing, which is the same number as this, so n must be a factor of m times x minus x naught. But those two numbers, m and n, were relatively prime. So if m is a factor of this product and it's relatively prime to n, m must be a factor of y naught minus y. If n is a factor of this product, but it's relatively prime to m, n must be a factor of x minus x naught. Okay, if m is a factor of that, then m times something is equal to y naught minus y. So I write y is equal to y naught minus m times k. So m times x minus x naught is the same number as n times y naught minus y. We already had that up here. We just wrote that y naught minus y is m times k. So n times y naught minus y is nmk. So m times this is m times nk. Cancel out the m and get x minus x naught is equal to n times k, or more specifically, x is equal to x naught plus nk. From the fact that a was the GCD of a and b times m, and similarly for b, I can write m is equal to a over the GCD and n is equal to b over the GCD. So x is x naught plus nk, but n is b over the GCD, and I get that right there. We also had y is y naught minus m times k, where m can be written as this quotient, and I get that right there, and that's exactly what we wanted. If x naught y naught is one solution, and I happen to find any other solution of x and y must be of this form where k is some integer. And this some integer k showed up back here. So now we have shown if x naught y naught form a solution to our desired equality, then any choice of x and y of this form will also solve it, but conversely, any solution of x and y must satisfy this form. So the set of pairs of this form is exactly the set of solutions to what linear combinations of a and b can produce their GCD. Let's take a look at an example. Suppose that 13 times 6 plus 11 times negative 7 happens to be the GCD of 13 and 11. This is true, but let's just take it as a given. I want to form the GCD of 13 and 11, and one way to do it is 13 times 6 and 11 times negative 7. Then let's find all solutions, x and y. Well, one choice of x and y was given to us, so we just apply the previous formula. X is the one thing I found plus the other coefficient 11 times k over the GCD, and y is the one factor that we were given minus the other coefficient of 13 times k over the GCD. The GCD of 13 and 11 is just 1, and here we have it. Any xy of the form 6 plus 11k and y is negative 7 minus 13k will give us a pair that will satisfy 13x plus 11y is 1. So k is allowed to be any integer at all here. There are, in fact, infinitely many solutions. That's really all there is to it, provided you can find the one solution to begin with. Okay, in this problem, we were said, suppose that you found 13 times something plus 11 times something else is the GCD. Then we quickly said, okay, well, here are all solutions to 13 times this plus 11 times this gives us the GCD, which is 1. So if you can find one solution, you can apply this formula and quickly get all of them. But how do I find one solution to begin with? Okay, Bézout's identity does tell us that there is a choice of integers x naught, y naught, so that ax naught plus by naught is the GCD. And once I find one solution, this formula gives us all of them. Okay, but our proof in Bézout's identity that this solution existed essentially relied on the Euclidean algorithm. So it shouldn't be surprising that we're going to modify the Euclidean algorithm to find one solution. And here is the title of this section, the extended Euclidean algorithm. Now, before we can present this modified or extended Euclidean algorithm, we need to introduce some notation about vectors from linear algebra, but we're going to do it very specifically for our context. So if you are not familiar with linear algebra or working with vectors, don't worry. We're about to go over all of it that we need. Suppose a and b are integers and they're not both 0. We're going to let the vector m comma n, notice that these are now in pointy brackets, so it's different from GCDs and it's different from LCMs. Okay, the vector m comma n is simply a shorthand way of representing a times the first entry m plus b times the second entry n. For example, if I had 4 comma negative 1, I have the first entry times a plus the second entry times b, or 4a minus b. This is just a number. Depending on a and b, it might change, but for a and b chosen, this is just an integer. The vector negative 4, negative 7 would be negative 4 times a plus negative 7 times b. This is just an integer. Conversely, if I happened to have 13a plus 2b, I can represent that as 13a plus 2b, the vector 13, 2. So vectors can correspond to linear combinations of a and b, and conversely, linear combinations of a and b can be represented as vectors. But note, it's just an integer. While it looks like a pair, m comma n, it stands in as shorthand for am plus bn, and at the end of the day, that is just an integer. So since it's just an integer, we can add them together or we can multiply them by other integers. So here's the first claim. This vector plus this vector can be done by just taking the first coordinates, m1 and m2, and adding them together, comma, the second coordinates, adding them together. In other words, one vector plus another gives you another vector where all you have to do is add the first coordinates together and add the second coordinates together. If you've taken linear algebra, this looks obvious because this is how vectors work. But what we're really doing is showing that this shorthand notation for vectors is consistent with how vectors work. Okay, so if I'm using this notation to represent this linear combination, we need to make sure that everything checks out. Well, m1 n1 plus m2 n2. m1 n1, remember, is shorthand for m1a plus n1b. That's what this vector stands in for. Similarly, m2 n2 is shorthand for m2a plus n2b. But now I have two terms with an a, so factor a out, and I have two terms with a b, so factor the b out. But now I have a times one number plus b times another, and in terms of vector notation, I would just write the first coefficient, comma, the second. And at the end of the day, yep, vectors add exactly like we think. The second claim is that if you have this vector and you want to multiply it by an integer, you simply distribute that integer to every coordinate. And it's a straightforward computation. The vector mn simply stands in for am plus bn. Distribute that k and then refactor as follows, and you get a times one number plus b times another. So I can write that as a vector of the first number, comma, the second. So if I want to add two vectors together, I can add them component-wise. If I want to multiply a vector by an integer, I simply distribute it. In linear algebra, this integer k would be called a scalar. we're avoiding that terminology because we're not really focusing on linear algebra here. But we're showing that this shorthand notation is actually consistent with how vectors operate. So vector notation is going to actually save us a lot of work in a few slides. So vectors can be added together or multiplied by integers in a pretty straightforward way. I would caution you that we're not developing any way to multiply vectors together. It's totally doable in this specific context because vectors represent a specific way of combining integers. In general, in linear algebra, multiplying vectors is a bit more tricky. Okay, also note, a is definitely equal to a times 1 plus b times 0. But hey, that's 1 times a and 0 times b. So I can represent a as this vector, and b can be represented as this vector here. So what we've established is a can be represented as a vector, b can be represented as a vector. Any sum of two vectors can be represented as a vector. Any product of a vector with an integer can be represented as a vector. And now the goal is find a vector that represents the GCD. So here's the extended Euclidean algorithm. Assume a and b are both positive integers. Let x be this vector and y be this one. These are both positive integers. Then the remainder, y over x, is another linear combination of a and b. Specifically, the remainder of y over x is y minus the quotient times x. Y is this vector here, that was our assumption. The quotient times x, but x is this vector here. Now, since vectors, distribute this constant across both terms and then simply compute the difference. m2 minus the quotient times m1, comma, n2 minus the quotient times n1. So the remainder of y over x can be expressed as a vector. A complicated to write one, sure, but it's still a vector. So whenever I have two vectors that represent two distinct integers, the remainder of the division can be expressed as another vector. So now I have two vectors for a and b. The Euclidean algorithm says instead of computing the GCD of a and b, instead compute the GCD of a remainder. But the remainder can be expressed as another linear combination of a and b. So the greatest common factor eventually appears as a single term. But as I apply the Euclidean algorithm over and over again, I'm taking the GCD of two things that can be represented as vectors. A and b can both be represented as vectors. This remainder can be represented as a vector, and so can a. Then this remainder can be expressed as a vector, and so forth and so forth. Okay? We start with two things that have vectors. Remainders can be expressed as vectors. So if I keep applying the Euclidean algorithm and keep computing remainders, everything that it generates can be expressed as vectors representing linear combinations of a and b, and the greatest common factor eventually appears in the Euclidean algorithm, and therefore the greatest common factor can be expressed as a linear combination of a and b. This was essentially how Bézout's identity worked. But what we need to do now, as we run the Euclidean algorithm, we just do a parallel computation to keep track of what linear combinations are showing up. Okay, we're going to separate a different video to run through examples of this because this is already close to 20 minutes long. Okay, so the next video will go through a bunch of examples of how to do this. So far, what we've justified, however, is that by running the Euclidean algorithm and using some vector notation, we're going to be able to keep track of what linear combination of a and b is eventually equal to the greatest common divisor.